In the final video of Section 2, we use our two-pan balance and algebra tiles to explain how division can be used in the preservation of equality. First, we look at our balance scales, and we remember the idea that whatever I divide one side of the equation by, I must divide the other. We will only divide by natural numbers that are greater than 1, so numbers like 2, 3, 4, but we have to be selective here. In order for our modeling to truly work and to demonstrate how division and the preservation of equality are linked, we have to be a little bit picky over the values that we choose. I'll explain that as we go through the examples. And of course, dividing by 1 does not change anything. Once again, our two-pan balance. Let's add in some masses. On the left-hand side, I've put a mass of 6 and a mass of 4. And on the right-hand side, I've put in a mass of 10. Our two-pan balance is leveled off because 6 and 4 does indeed give us 10. If we look at the numbers 6, 4, and 10, I want you to think of it like this. Can we take half of all of these masses so that the resulting mass is a whole number? And the answer is yes. So I could essentially divide by 2. If I ask you the question, though, can you take a third of all of these masses nicely? Well, I'd be able to take a third of 6, but taking a third of 4 would result in some difficulty because I would not get back a whole number mass. Similarly, with the mass of 10, if I tried to take a third of that, I would not get back a whole number mass. So here we would not divide both sides by 3. What I am going to do is what I said initially. We're going to divide both sides by 2. So I'm going to take half of what's on the left-hand side. Half of 6 would give us 3, and half of 4 would give us 2. Of course, my scale tips down to the right when I do that because I have less mass now on the left-hand side. So the 6 and 4 has been replaced with a 3 and 2. In order to balance things out, I need to take half of what's on the right-hand side. And half of 10 would give us 5. 6 plus 4 cut in half is equal to 10 cut in half. In other words, we have divided both sides by 2 to maintain balance. Let's consider now a linear equation. 6 plus 3h equals 9. So let's get a representation of that. A mass of 6, 3 hexagons for my 3 variables, and on the right-hand side, a mass of 9. If we think about what we can try and divide both sides by here, dividing by 2 this time would result in difficulty. The mass of 6 wouldn't be a problem, because I could easily take half of that. But when I get to the 3 h's, and when I get to the mass of 9, if I try to take half of those results would not be whole numbers. So dividing by 2 here, not an option. However, if I think about dividing by 3, the same idea as taking a third of everything. Can I easily take a third of 6? Yes. Can I easily take a third of 3h? Yes. Can I easily take a third of 9? Yes. All of those results will give me back whole numbers. So in this case, we're going to divide our equation by 3. So if I divide the left-hand side by 3, a third of 6 is 2, and a third of 3h's would give us 1h. So we're left with 1h on the left-hand side and a mass of 2. Our two-pan balance is no longer balanced because we have removed some mass from the left. To balance it out, we need to do the same thing to the right-hand side. So if I take a third of 9, we get back our mass of 3. Whatever we do to one side, we must do to the other. Our equivalent equation then becomes 2 plus h equals 3. And now we look at our algebra tiles. Whatever I divide one side by, I must divide the other. Linear equation is 5x equals 10. let's represent. So on the left-hand side, we will have 5 variable tiles, and on the right-hand side, we will have 10 units. Now, what are we going to divide by here? If I try to divide by 2 or cut everything in half, that's going to create trouble on the left-hand side because I have 5 variable tiles. The right-hand side, I'd be able to cut those in half, no trouble. But I got to be able to do it to both sides. If I try to divide by 3 or take a third of everything, definite issues. If I try to divide by 4, take a fourth of everything, going to have trouble. How about dividing both sides of the equation by 5? I'm taking a fifth of everything. That is doable. If I take a fifth of 5 variable tiles, I'm left with 1 variable tile. If I take a fifth of 10 units, I'm left with 2 units. Another way you could look at it is that if you have 5 variables and you have to put them into equal groupings, you would have 1 in each group. If you have 10 units and you have to put them in 5 equal groupings, you would have 2 units in each group. Symbolically, what are we left with? X equals 2. So this is another one of those cool examples where in creating an equivalent equation, we actually also solved it. X equals 2. And our final example, let's look at 4m plus 8 equals 12. If we're using algebra tiles, we're going to represent first. So on the left-hand side, I have 4 variables and 8 units. And on the right-hand side, 12 units. In this example, we have a couple of possibilities with the numbers 4, 8, and 12. We can divide both sides by 2. Everything here we can cut in half nicely. Dividing by 3 or taking a third of everything would be problematic. 4 is a possibility because 4, 8, and 12, each of those numbers are divisible by 4. What are we going to do? We're going to divide both sides of the equation by 4. So if I take 4 variable tiles and put them in 4 equal groups, I will get 1 in each group. If I take 8 unit tiles and put them in 4 equal groups, I'll get 2 in each group. And if I take 12 unit tiles and put them in 4 equal groups, I will get 3 in each group. Here we take a fourth of everything on both sides. A fourth of everything on both sides. Symbolically, we are left with m plus 2 equals 3. 1 variable tile, 1m. 2 unit tiles plus 2. 3 unit tiles equals 3. This would be our equivalent equation. And now I'd like you to proceed to the activities for Lesson 2.